Thank you, everybody. We're going to hear a couple more beeps as external members or community members are joining. But thanks for joining us, kicking off some more community calls. I know it's been a while since we've had them. We've had a lot of engagement through gatherings and other avenues, but wanted to kick this off with a special topic that is really close to my heart. I know that sounds weird, but you know, we've been waiting for CoreOS layering for a long time. But before we get started with that, I want to give a couple community announcements, and I will paste the notes doc again into the chat. But registration is open if you haven't been to our gatherings. Registration's open for both our OpenShift Commons gathering on October 18 at All Things Open. That's in Raleigh. And then also for KubeCon Chicago. If you're coming to KubeCon, registration's open for OpenShift Commons gathering on November 6th. And that always goes fast. So sign up if you know you'll be there. Also, I'll put in here, you know, if you aren't a community member, make sure that you join up, but you don't have to come to our meetings. We're just happy that you are here. And again, our agenda today, we have our product management from Red Hat CoreOS, Mark Russell, and then also wonderful engineers. We have Zack, Zlotnick, and Colin Walters. So amazing. And Colin has spoken at a gathering before, actually. Yeah. And so after that, if you wait till the bottom of the hour, Gunnar Hellekson, who's our VP and GM of Linux, he's going to be here and he's going to stop by and talk about Rel and OpenShift and platform consistency. So stick around. And with that, thank you all for being here. And Mark, I don't know who wants to kick it off, but please.
I will. Yeah, no, I'll grab it, but I am going to hand it directly to Colin Walters.
Awesome. Yeah, thanks. So as Estelle says, you know, we're really on a journey, and I was there kind of at the start of the transition from OpenShift 3 to OpenShift 4, and you know, as any of our customers or OKD users who have come along, you know, it was a giant change. I like to say it was a tectonic shift. Because, you know, we took the CoreOS tectonic Kubernetes distribution. It was huge, right? And you know, I'll give you something spicy. I remember someone saying at the time we weren't sure it was going to work, but it did. You know, there's still design things that we want to change, and this is part of them. But you know, for example, the opinionated installer is just the foundation of all of our CI now. You know, making sure you can spin up a cluster quickly. The cluster version operator, and especially the machine config operator, giving you Kubernetes native visibility into the status of the cluster and the OS state. Being able to change your kernel arguments with kubectl. It's a big deal, right? A lot of change. Ignition is has become a foundation of a lot of things that we do, because for OpenShift, being able to make sure that we work seamlessly across cloud and bare metal in a symmetric, consistent fashion, we've just built up a lot on top of that. And yeah, as I mentioned just a couple seconds ago, the machine config operator being that entry point into OS management and upgrades and configuration was a giant change, and one that we've built on a lot. And the CoreOS layering that's coming, it's already landed in 4.13. We're going to demo more, has evolved significantly since then.
So yeah, just to back up what Colin was saying, you know, CoreOS, Rel CoreOS in this case, brought an appliance-like container optimized edition of Rel. I like to think of it as an edition of Rel. It's the same OS. We had image-based updates tested and versioned with the cluster. We had a strong principle enforced that all workloads beyond that appliance base, whether it was a third-party agent or a user workload, all of that should be run as containers. And we kept that as a strict rule. And in many cases, it worked great. It helped us bring a vastly simplified and more reliable update process to our customers, but it wasn't always a perfect fit. So Over time, we've had scenarios come to us from partners, from customers directly, that were difficult or impossible to do with CoreOS as it had been managed so far. Requirements might be like an additional RHEL package that made sense for a subset of customers, but wouldn't make sense for us to add to the whole base. That's the same image that gets shipped to all customers, and every package that we added incrementally adds to the size, adds to the attack surface, and anybody who's managed a software project will know it's very difficult to remove things once you've added them. So we had our reasons for saying no, but what about these valid use cases that were being brought to our attention? Other things like a security agent that's required by your IT operations that hasn't been containerized by the vendor, your server manufacturer's system inventory agent, or an out-of-tree kernel driver. Maybe just something that you needed temporarily. It wasn't easy to do. At the same time, we also heard from some customers that managing their node through machine config objects had a bit of a learning curve. It could be challenging in normal circumstances, especially if you're new to it, but especially in urgent cases. So putting this together, it became clear over time that we had to soften some of our stances. But if we go back to OpenShift 3 users had complete freedom, essentially, to manage their RHEL nodes. But we knew from experience, and maybe you do too, that came with a lot of complexity. It made upgrades much more difficult. So how could we keep the virtues of this cluster-managed, image-based OS and still allow for customization? That's our subject today. But before I go to the next slide, I should stop and note that if you prefer your current RHEL CoreOS service, change nothing. The machine config API is not going anywhere. CoreOS layering is fully optional. And I should mention that it's day 2 only, but we'll get to what that means and the implications later. So what is it? The central idea here is we're putting the OS root file system in a standard OCI container. Simple idea, but it's just another disk image format, right? But it's not just another disk image format. It's the same industry standard. It's a format that works with the same industry standard tooling that you're already using in and around your Kubernetes environments. They're all built to work with containers. And suddenly all these things now work with your OS images, your container registry, your container security scanners, build tools, pipelines, whatever GitOps regime you have going. It can integrate fairly easily. And with the skill sets of, not to harp too much on the DevOps movement, but which is not necessarily one person, but with DevOps and site reliability engineering, bringing those skill sets closer and closer over time, it seemed really perfectly logical to close that gap in our tooling between how we manage apps and how we manage infrastructure.
Yeah, though I think it's always important to look at the technical side and clarify the operating system is not actually running in a container. We're not making Podman or Cryo actually PID one. We're just using the OCI standard containers as a customization and transport format to update the root file system. We do need to support actually running it as a container in order to use it as a build base in production. However, it's not intended to be used as an application-based image. Continue to derive from the RHEL UBI image for applications. And the way this is implemented at a technical level is it's effectively a new storage backend for containers that maps to what we were doing before with OSG. And this is the way that upgrades are implemented. It's the reason that upgrading into this is seamless. So on the wire, we use the standard containers image library, the same thing that's used by Cryo and Podman. So things like the Etsy containers.conf, honoring offline mirroring, all of that's respected.
And I'd like to mention that it is handy that you can run these as a container. If you want to do simple inspection or you want to run tests, but you can do it more cheaply without having, you could do a functional test that now you don't have to fire up a VM to make sure that it's working. The demos will definitely be better than me talking about code on screen, but they'll indulge me for a moment. I think this helps frame some of the other slides and kind of brings it home. Here's an example based on Fedora CoreOS. Let's see what this Docker file says. First, it pulls in the latest Fedora CoreOS stable base image and copies an Ansible playbook. Then we install firewall D and Ansible, after which the playbook is executed in offline mode. This one happens to open the ports for OCP. And then we remove Ansible, delete cached repo data, which is just noise in the image, effectively, and then we commit the final container image. So this is a great example of how we're now opening up machine configuration to your favorite tools again. That could be Ansible, that could be another configuration management tool, it could be Shell, anything you can run in a container build, really. But why are we removing Ansible? That's because we don't need or want to run Ansible in place on the node live. Think about the node like a container image. You don't exec into active containers and update them. You redeploy a new container based on a new image. So under this model, if we wanted to change the open ports, for example, we would edit the playbook, rerun the build, and then the host would rebase to these new settings in the new build. Now I'm going to zoom out for some OpenShift context. This is it's kind of my schematic here of the off-cluster build. Simplifies things a little bit. This is GA already. It's released in 4.13. In this setup, the administrator provides a build environment, a container registry, and of course, whatever custom content that they define in their Docker file or container file, if you like. After completing a successful build, you push the container to your registry. Now, at that point, optionally, you can run any sort of arbitrary testing you want, automated or otherwise. Because you're using a build process, you do at least get a basic integration test, right? You know the build has succeeded, all the package installations, the dependencies are met, the kernel driver installs cleanly. Otherwise, right, the build will fail, and you'll know that right away. Whether you add tests to that is up to you, but you could add functional tests. There might be scripts that your security team wants to run before approving that image in production. You could run the container through the standard security scanner, the enterprise standard scanner that you might use. You might check for certain configurations. In any case, once you're set and approved for rollout, you apply a small machine config that tells the machine config operator to apply that particular image to the pool that you assign. We're still, so you can see, hopefully you can see, we're still inhibiting the configuration drift that we saw so often with OpenShift 3. We're having full customization, but we're enforcing consistency across pools of machines by reliably rebasing them to a standard image. So I hope that was straightforward conceptually, but as you can see, you can make it as complex as you need it to be for your requirements. Now, here's the make it so version. The battery is included. Let's look at the on-cluster build option, which is coming as a dev preview in 4.14. Now, instead of sending the Docker file, to a build tool, we're going to jam it in some YAML. After all, this is Kubernetes, and then we're going to apply it to etcd, and that's when the MachineOS builder component steps in, affectionately known as the mob, unofficially. Don't tell brand. With automatic builds enabled, the MachineOS builder will know to rebuild when you click update in the console or if you use OC ADM at the command line. The MachineOS builder will pull in the correct version of RHCOS that matches the target release of OCP that you're updating into. It'll run the build using your customizations and roll out the completed image to the pools that you specify. Okay, one more before we get to the demo. Hopefully you can see again, this is still an image-based edition of RHEL. It's not a varying assortment of general purpose packages. It's some range of patch levels. Each image is a specific set of packages at a specific revision level shipped as a unit. And crucially, those are the units that we test every day in our CI. And it's still the same appliance like images before. You can call it immutable, which is a term that tends to stir a lot of discussion. Whatever you like to call it, it's still applied to the node disk as a read-only /user partition. The difference now is that you can layer your own content into the read-only image. So in many respects, you can think of the RHCOS node base image a lot like UBI or another application base image. And the support model is similar in this case, right? Red Hat is, of course, responsible for the base image unit. Bugs happen, but the base image should be expected to be well tested and working. When you add extra RHEL packages, we have shared responsibility, right? Because of course, we as Red Hat, we're responsible for bugs in those packages, but at the same time, they're not standard parts of OpenShift. So you have to take some care to configure them in a way that they don't break or degrade OpenShift significantly. And of course, there's your own custom third-party content. And in this area, we're going to be no different than RHEL. We support the installation methods, but after that, our standard third-party support policy applies, linked below in the slide. In some cases, you may be asked to disable a particular configuration of integration or customization if there's reason to suspect it's related to your problem. I don't think this is normally controversial in practice. It's really just standard troubleshooting techniques. All right, enough slides. Let's see how this really works. First up, we're going to have a Colin with the demo of off-cluster builds, and then we're going to have Zack preview the Machine OS builder.
Hey, Mark, really quick.
Sure.
We have a question in the chat. So before you go into demo, sorry, Zack.
Not at all.
So Tom, would you like to ask, or I can go ahead and ask for you? Just giving you the opportunity.
Go ahead. That's fine.
Oh, okay. Sorry. You already answered the question.
So Tom asks, you mentioned security scanners, and really this is one of the things that excites me about the layering too. So I'm glad you asked this, Tom. So he asked, what about performing forensics on the node or running forensics container checkpointing? And will the way customers perform forensics still be supported?
I can take part of this. I think, I'm curious if Mark has more to add, but basically, if you have a workflow that operates today in scanning a node, that will continue to work. It will be mostly invisible. And we needed to do that in order to have upgrades be seamless. But a new power that is gained with this, and even without layering, you can pull the OS image that we ship, and you can run any tool, for example, Claire, to scan it for CVs, right? And especially when you get into a layering world where you might have a Linux team that's adding content to your node, if you have an existing CI pipeline that takes your application container images, you can use that same flow for the OS container and before shipping it out to production clusters.
That was it. I was going to say, I'm glad that Colin confirmed what I suspected, which is it should be transparent. But that's a great point. So without further ado, and I think this is probably was taken care of already, but just that the container registry is separate. We're going to allow you to have an on cluster one, but if we know a lot of customers have their own preferred and corporate standard registry, so we're going to work with that, whatever you like. All right, so let's go to the demos. I will full screen this.
Hello, everyone. In this demo, we are going to be looking at this example of a container build file that applies an override kernel on top of RHEL CoreOS. In this demo, we're going to be using OpenShift 4.12. The top-level goal here is to enable a container-native build process and deployment process for hotfixes and OS customization. So we have a newly created Git repository here in RHCOS image layering examples. And let's go ahead and look at this container build file. In this example, we are pulling from a hard-coded digested pull specification. Now, as this says, and is mentioned in the documentation here, you'll want to run this command to find the correct base image for RHEL CoreOS for your cluster version. At the current time, for kernel override specifically, this command invocation is required. In the future, it probably will not be. And then here's the heart of this. As you can see, we're pulling from CentOS stream. Now, that's one valid scenario. Perhaps you hit a bug in in this case, we're running Rel 8.6 as part of OpenShift 4.12, but perhaps you want to check whether the kernel bug is fixed in CentOS Stream. You can use this to pull that as a fix. But this is kind of, again, a stand-in for maybe you get a hot fix from Red Hat for a specific kernel bug, or to revert to an earlier shipped Rel kernel until a bug fix can be provided. So this is, again, just a stand-in for arbitrary kernel replacement. Now, what I'm going to start here is to demonstrate. I've built this this container image beforehand, and although I can demonstrate how that works here, yeah, it's a Podman build. Now I pushed the container image to this registry, so I can image. You know, again, it's just a standard container image here. I can inspect it. Now, what I needed to do is, currently in OpenShift, to deploy, you need to get the digested pull specification. So right here you can see we have this handy Scopio command that, given a latest tag or a tagged image, gives you the digested one with the SHA. And then, per the documentation, I've created this machine config file. I'll demonstrate here. And now I'm going to go ahead and apply that. But first, let's look at, let's see, get cluster version. I'm just demonstrating, get nodes wide. And what I want to demo now is have this handy little custom columns command that just shows the nodes with their kernel versions. So we're going to go ahead and create this machine config. Now, what we should see here is that in just a couple seconds, we should get a new rendered config from the MCO that includes our new target container image. Let's go ahead and look at that again. All this is a small machine config that says pull and deploy this container image. So again, the idea is every tool and technique you know from building containers can be used to apply hotfixes or overrides. So that could be IP tables, it could be anything, or any extension. And we have a number of examples in the repository. So what we should see now is the rendered worker node is starting to roll out. And this will take a couple minutes. So in the meantime, what I want to show is, I have a handy command here. So we can also run the stock image as a pod. And let's talk about that for a sec. Notice we're only rolling out the hotfix to the workers. So I'm going to run this command to get the stock OS image. And I can do this in a couple different ways. So this is the stock image. And we can run. We can run it like this. And we can use its rpm-u kernel. And so this image, this stock image, contains a kernel. Format. And in this, we'll just show that the kernel came from Red Hat. In our demonstration example, we're attempting to apply a hotfix kernel from CentOS Stream, a newer version. Now, of course, this kernel that happens to be in the container is not the same kernel that is on my host, right? We're running this container image the same way every other container image is run. In this example, I have a Fedora-based workstation, so the kernel I'm using here is from Fedora. Now, what we can also do is run my modified container as a container, and we'll just run those same commands here. And when I run this, when I run rpm-u kernel, you'll notice the version is different than the one that's in the stock base image. And here, just to verify, when we look at the vendor who built it, it was built from CentOS Stream. Now, we should start seeing the rollout of the custom kernel to nodes. It looks like one of the workers is in scheduling disabled. And let's look at the handy one with the kernel version. So this is still in the process of rolling out. So at this point, we just need to wait a couple minutes and we should start seeing that roll out. All right, so we just waited a minute here. Let's go ahead and run this custom command, which will output the node names along with their kernel version. And as you can see here, one of our worker nodes has already reverted to that hotfix kernel. So at this point, the machine config operator will continue to roll out the hotfix to all of our worker nodes. But one of the key powers here is that at some point in the future, imagine that you've done and it's actually, let me back up. At this point, the kernel version is pinned, and that means that cluster versions from OC8M upgrade will not upgrade the OS on the nodes. We have pinned the operating system state. But in the future, if you upgrade to a newer OpenShift version with a newer default image that you know contains the fix, what we can actually do is simply OC delete on our kernel hotfix, delete machine config on our kernel hotfix, and at that point, the machine config operator will revert to the stock kernel image. So this demonstrates how we can take a standard container build file and use it to deploy changes on top of Rel CoreOS.
Okay, next demo coming up with Zack.
Hello, my name is Zack Zlotnick, and I am a software engineer on the OpenShift Machine Config Operator team. Today, I am very excited to share with you on-cluster builds for layered images, which is now available as dev preview in OpenShift 4.14. To begin experimenting with on-cluster builds, there are some prerequisites such as secrets, config maps, and a container registry that one can push and pull their OS images to and from. For the purpose of this demonstration, I will use an OpenShift image stream, which is fully self-contained within my test cluster. However, one could very easily use an external image registry such as Quay for that purpose. So let's talk about just a couple of the prerequisites. Let's talk about the machine config pool that we'll need. We're going to create a new machine config pool called layered, and then we're going to opt that in by adding a label to it. The next thing that you'll need is you'll need a config map that tells the build controller where to pool the images to and from and what secrets to use for that purpose. And so with that in mind, we have this for the base image pull secret. We have this for the final image push secret, very self-explanatory for the purposes of our demonstration. And then we have the final image pull spec, which in this case points to the in-cluster image stream. And just a note about the tag here, the tag itself latest will be ignored by the build controller. Instead, each built image will be tagged with the name of the rendered machine config that was used to build it. And so the last thing, and this is purely optional, is a config map that contains any custom Docker files or custom content that you would like to inject into your custom OS image build. And so with this in mind, there's a one-to-one mapping of machine config pool name to Docker file. And again, as I mentioned, this is optional. I left these two blank purposely just to show that they are indeed optional. You don't even need to provide them if you're not trying to target that pool. And so just a word about what our Docker file does with some colorful syntax highlighting here is we use the CentOS image to install the extra packages for enterprise Linux stuff so that we can install packages from that repository. We will also pull the YQ utility, which is a command line tool for parsing YAML, we're going to pull that directly from the image that they release. And then finally, we're going to put all the extra package enterprise Linux configs and all of those things into our final image, which we will then use to install calsay and ripgrep. And finally, we'll download a custom cal file that will include within our base OS image. And we'll show that in just a minute, in just a few moments here. So without further ado, let's apply all of our YAMLs and get this process started. So if you'll note, we created all of those things, but we now need to opt our layered pool into the on-cluster build process. So to do that, all one needs to do is add this label here, add this machine configuration.OpenShift label. I wrapped it in a shell script just for brevity because trying to type out something like that during a live demo is kind of difficult. Okay, so now that we've done that, we can now see that within the machine config operator namespace, a couple of new pods have been started. We have this machine OS builder pod, which is where the build controller itself runs. And then we have this pod here, which is our builder. Now, before we go in there, we also have a couple of new config maps that got created. We have this Docker file config map that has our rendered Docker file in it, as well as the custom Docker file content that was provided through our config map. And then we also have this additional config map here that contains the current rendered machine config, which has been compressed and base64 encoded. And so with that in mind, our build will have those config maps attached to it, and it will read the machine config from that config map, as we're doing right here. It will decompress it. It will run ignition on it to apply all of the content that's in that machine config to the container that's being built, as you can see right here. And then once this process completes, we then move on to the custom content that we've added. So right here we're installing the extra packages configs. And now that we've done that, we're pulling YQ, and now we're copying everything into the final OS image, and we're running RPM OS tree to install the two packages rip, grep, and calsay. And so now that's completely built, and now we're pushing that to our in-cluster registry. And we're all done. So now you'll notice that with the machine config pool that we created, we now have a new annotation called newest image equivalent config. And this points to the pool spec for our new OS image. And so right now, we have an empty machine config pool that has an image that's ready to go and ready to be applied to all of the to any nodes that are added to that pool. So let's go ahead, let's grab a node and let's add it to that pool. And so again, I've got a small shell script that I wrote that just adds the appropriate node role to that. And then now what we'll see is, so now we should see that our brand new node will now apply the latest image, or will now consume that image. As you can see here, we're now starting the transition to our brand new OS image. And so the way that this works is we apply a desired image annotation to the node. And so this is very similar to how machine configs currently work. There's a current config and a desired config annotation currently. And so this will be augmented and added onto with the addition of both a current and desired image annotation as well. So right now, our machine config daemon is cordoning and draining our node. And once it does that, there it goes. It's now RPM OS tree is now pulling that image down and applying it onto the node's disk. And so now the machine config daemon is now initiating a reboot to finalize the process. So while that's happening, you can see here that, as I mentioned before, we now have this desired image annotation. And once the image has been rolled out, we will have a corresponding current image annotation as well. And this is these will be provided in addition to the current and desired config annotations as well. So let's go back to our node and let's see if we can watch the machine config daemon finish the processor and finish the job. And so there we go. So now we can see that. So now we can see that our PMOS tree is finalizing everything. We can see that the MCD itself is now completing the update from that to our new image. We've uncordoned our node and we've transitioned from working to done. And so now if you look at the node object again, you'll now see that there is a current image annotation that matches our desired image annotation. And so with that in mind, because we have all of these wonderful tools that we just built into our new OS image, it would be a shame if I didn't show them. So let's do OC debug into our node. And once it schedules the debug pod, we'll cheroot into the host so that we can make use of its binaries. So now we should see that we have the YQ command is available, and we can parse the current config that's on disk with that. It understands JSON too, so not a problem there. We also have the ripgrep command, which ripgrep is probably one of my favorite utilities. And so we can ripgrep for, say, the word podman in our etc directory. And there you go. And then finally, we have calseg. And here's a very special message about that. Rocco from Rocco's Modern Life would like to tell you that update day is no longer a dangerous day. Thanks for watching.
All right, that was awesome, and I wholeheartedly endorse Rocco's message. Let me second that. So let me just try to wrap some things up. Here's a quick checklist for why you may pick one or the other. And Gunnar, I think you're right on that. Off cluster building is great. First of all, if you need something today, it's supported from 4.13 on. Again, you need to be kind of willing to take responsibility for the OS updates, but you may want that granular level of control. If you need to integrate with custom test pipelines or CI/CD systems, things like that. Or perhaps if you think that it makes more sense to build in one place but run in many clusters. If you're a sysadmin managing dozens of clusters, maybe doing a central build makes more sense. Whereas for Machine OS Builder, play around with it starting 4.14. This is the easy button. Zack showed you there's a little bit of setup work, but once you do that, you're now ensuring that OpenShift upgrades will automatically be integrated with your custom content. And I also think it's the perfect solution for people who don't know yet that they might need it. So you have a hardware device, is intermittently seg faulting, the driver is intermittently seg faulting, and you have a test package from your vendor. Not even the final fix, just try this and see if it helps. Well, you might not want to get into the whole business of creating a build environment and doing all that. You just want to add the package, and I think that's Machine OS Builder is going to be perfect for that. Just really quick, very quick, because this is just a repeat slide. This is like the take your vitamin slide. You have the wheel, you have responsibility on off cluster updates. We believe staying up to date is a virtue, and that will benefit you, not just us. And of course, Red Hat support policies are linked. Day 2 only is a key caveat. So if you are looking for to inline some drivers for cluster bootstrap and new node scale out. I need to specifically mention that, right? Like any new node still works off of pristine boot images for now. The team is working hard. It's at the top of the development list priorities. Hopefully you'll get something tangible to play with at around 4:15 time. Put a lot of asterisks around that, but that's what we're aiming for. And what's next is bringing the mob to GA, console integration to make it even easier to get started. And then we want to hear what you all think, and what you hear from, what you think, what maybe your customers in turn think, and if that's appropriate. Should there be declarative interfaces? Do you like machine configs and you're invested in them and you'd rather define your repos and your add-ons through a machine config? Let us know. And what other knobs and dials you'd like to see on cluster builds. And with that, I know you're all busy folks, and thank you for everybody. We ran a little bit over. Apologies for that, Gunnar. We really hope it was worth your time, and thank you again. Karina.
Thank you. Thanks, all of you. That was great. It was fantastic. And I know we only have about 15 minutes. So, Jerry, thank you for your question. I'm going to have Colin and the others hopefully answer that in chat. And Gunnar, since you're here, and thank you for joining us. Really appreciate it. If you want to go ahead and dive in and tell us your thoughts. And
I had a whole thing ready to go, but if we got 15 minutes left, there's kind of nope. All I'm going to do is filibuster everybody's questions. I would feel like the stars of the show over here. Mark, you're welcome to go over time. Just keep in mind that merit and equity nominations are coming up, so too bad for you. Hi everybody, I'm Gunnar. I'm the GM for Rel. I was going to give a whole talk on kind of technical consistency and like the architecture of the operating system and stuff like that. But I have a feeling that this crowd probably has more follow-ups to do with Mark and Colin. That's probably a time better spent. It's fine.
well, let me take a poll from the community. What do you think? Should we see if Gunnar can go through his talk really fast, if he would so choose, or keep going on Red Hat Enterprise Linux CoreOS? I keep missing out on the Enterprise Linux, and now I have to include it for you, Gunnar. Sorry. Okay, well, if nobody is going to speak up, I'd love to hear from you, Gunnar, if that's okay.
Yeah, sure. Yeah.
And give your...
Happy to do that. All right, let me find a screen to share. Okay. So actually, I think this is the first time I've spoken with this group. It's nice to be here. I wanted to spend a little bit of time and talk about how we spend a lot of time, I think, talking about OpenShift and its reliance on Rel and all the various ways of managing CoreOS. Mark, Russell, Colin, like Zack, you all do a great job at managing these things. It moves in the other direction too, in that in Rel, we also think about like how do we best serve OpenShift, right? So it's actually a two-way relationship. And I wanted to talk a little bit about how we think about that. So we'll start first with the mission statement for Rel, which is, it's funny, we've been doing Rel for like 25 years and we never really had a mission statement until like 2 years ago. Like we finally decided, we should probably go ahead and make one of these because we're grown-ups now. So the first part of this is that we're a source for safe and reliable Linux innovation that makes your workload successful. That sounds like pablum. That sounds like regular marketing stuff. But crucially, the word distribution does not occur anywhere in this text, because Rel is not actually about being a Linux distribution. We understand it in a kind of a more expansive way. The second part of the mission is that we are everywhere that you need us to be. And this is where we talk about the breadth of hardware platforms that we have to support and that we want to support, right? Just from a commercial point of view, it is very important to us that Rel run everywhere somebody cares, because anytime we can't support a particular hardware platform, that gives somebody a reason to not use us, and it undermines the value of standardizing on our platform. right? So we always want to be wherever somebody wants us to run. And then the third piece is that we serve the portfolio, as I said, in particular serving OpenShift and the larger Red Hat ecosystem. So all the software and application providers, we're supposed to be helpful for them too, not just for the sysadmin. So with that in mind, this is I went back into Karina asked me to put this together the other day, and so I went back into the vault. For those of you who know Ben Briard, this is actually a bastardized version of a slide he created like 5 years ago. And so this is actually how we think about RHEL, I think, internally, at least on the product management side. At the very bottom level, you have all the kind of physical infrastructures we have to run on. So that's like the physical hardware, virtual hypervisors, private cloud, public clouds. On top of that, the next layer up is like the actual OS stuff, which is like the kernel and a very, very small number of packages, which actually constitute most of what that is for is actually solving the hardware problem, is actually providing the enablement for the particular hypervisor or the particular microarchitecture that you're running on. So it's x86 or ARM or PowerZ or whatever. Then there's a layer up from that, which is actually, let's call it the compatibility stuff. And this is actually, little pro tip here, this is actually what makes a major version of RHEL different from another major version, is the choice you make about your glibc, libgcc, PAM, libxml. It's actually a very finite list of packages that constitute what we internally call the ABI, or the binary interface, right? This constitutes the promise. This is the thing that is going to be stable, famously for RHEL's 10-year life cycle. This is the thing that is going to be stable. Other things are going to change, maybe at different rates, but we are going to bend over backwards to make sure that if something operates on .0 of RHEL 9, that we'll be able to operate on .10 of RHEL 9 without modification. And that's where this ABI compatibility promise comes from. And this is important for us as a platform because in the same way that the kernel is kind of where we collect the hardware ecosystem, the ABI is where we collect the application ecosystem. Okay, that would be enough. That would be all we needed to do if all we cared about was running applications and hardware, but it turns out people actually use this stuff. And so there's a whole nother layer of useful stuff, I think. And this morning, I think I call it like, let's call it node management stuff. And that's like the bare bones, like, SSSD, rsyslog, OpenSCAP, guest agents, your favorite virus scanner. That's all there's that layer on top, which actually comprises the third management promise that we make. So we have a stability promise around hardware, which is fulfilled by the kernel. We have a stability promise for applications, which is fulfilled by that ABI. And then we have a kind of a management stability promise around that kind of useful stuff layer, that node management layer. Because if every time we had a new minor version of RHEL, you had to completely retool your management, we wouldn't be much of an operating system. And so we have both an explicit and an implied set of promises that the management interfaces are going to be relatively stable. These become extremely important when we later talk about our interaction with OpenShift. And then finally, we have, let's call it the runtime stuff, right? You got your Rubies and your Pythons and your PHPs, and I have an unending backlog of runtimes that people ask me to run. Any guesses as to how much software is in RHEL? How many packages are in RHEL proper today? Anybody guess? Just throw your guess in the chat. Number of packages. Any guesses? Colin, you don't get to guess, Colin. You know the answer. It's 13,000. So if I stack all this stuff up together, I have 13,000 packages. And does anybody have a guess as to how many packages are at that compatibility stuff layer and below? It's like 200. So Gunnar, what are you doing shipping 12,800 packages that are not operating system packages? Like, why would you do that? And the answer is because you all asked us to. It's your fault. Every time we do a new release, we look through a list of people are constantly asking us to ship new packages. And it's not because someone somewhere decided that Firefox was an essential component of an operating system. It is not because tmux is an important part of the operating system. It's nice to have, but it's not essential. People ask us to ship the software because they understand that RHEL is not just an operating system. It is also a source of trusted software. And so every time you ask someone what every time somebody asks us for software, I love it when people ask us to ship software because that means they trust me to take care of that piece of software for them. And every time I add a package into RHEL, it enriches the overall RHEL experience, right? Okay, so let's call that all the runtime stuff up there. That's what let's call that the OS as supply chain. Okay, so architecturally, this is kind of how we think about RHEL. Now I get to go do that every 6 months for the rest of my life. And if you put the so all the RHEL folks are laughing at this. So if you line up the life cycle on this, at any given time, there are between 14, depending on the time of the year, there are between 14 and 17 RHELs running concurrently at any given time, which means that for every bug fix that we make or every patch we have to basically backport it 14 to 17 times every year. Okay. This is extremely valuable in ways that I hope you all immediately understand, right? This is extremely hard work. A lot of it is very boring work, but it is very important that we do this work, because if we did not do this work, the burden falls on the application developer to accommodate all the different kinds of packages and all the different security bug fixes and all the different bug fixes and all the possible combinatorics of 13,000 packages, right? We do that on your behalf, okay? So then containers come along. And containers basically, I mean, you guys have seen presentations like this before. You see, you have this carefully architected, beautiful system for managing all the complexity of 13,000 packages, and then some Nimrod comes along and dumps a blob of binaries onto the person's system and says, "This is," in the form of a container, and says, "This is rad. Go run this," right? And this was a existential kind of trouble for us over in the operating system business, because we're like, well, what is the role of the operating system if we just have these random binaries or a customer built binary, it just drops on top of a host, and like what is the value of the operating system in that case? And the answer became clear pretty quickly, is that once is fine, but lots of it simultaneously becomes a huge problem, because as I said, if you cannot standardize at that platform layer, you are not making a problem go away. What you are doing is moving the problem into the application. There's a reason why the operating system accumulated 13,000 packages. It's because people wanted to offload all that complexity onto one thing, standardize on a platform. To the extent that containers ignore the platform standardization opportunity, then they are taking on an unneeded burden for maintenance and patching and life cycles and all the rest of it. Does that make sense? Everybody give me a thumbs up. Anybody who doesn't work for Red Hat, give me a thumbs up. Okay, great. Thanks, Dan. Appreciate it. Okay. All right. Mindful of our time here, so I'm actually gonna stop here just for time's sake. But I'm gonna draw a boundary around this. So Mark and Colin and the rest of the team do a ton of work on CoreOS and the construction of UBI, and we believe that the reason for CoreOS, the thing that is magical about CoreOS, is that we have been able to take, as Mark said earlier, the exact binaries that run through our exact CI system. This is literally the RHEL content. This is not some special spin of the RHEL content. It is actually the RHEL content that has gone through all the rigor that I just described. And we're able to put it into a very consumable format. And I don't know if Mark discussed this earlier because I joined late, but my dream, at least, is for RHEL CoreOS is first a packaging. It is characterized first by the packages that it includes. It is also characterized by the way in which it is packaged through RPM OS tree, and then plus some extra special magic. What I would like to make sure of over the long term is that I want people to benefit from all of the work that we did in RHEL, and I think, and one thing that I'm excited about in the layering is that this allows people to take advantage of that standardization opportunity without sacrificing or having to hand spin or hand build anything. And to the extent that RHEL can make it easy for you to take like basically one blueprint of something and create your own CoreOS out of it, that allows you to get the customization that you need because you really care about virus scanning or whatever, or because you really need to go support some weirdo HP agent, but also take advantage of all that platform consistency that we have been successfully delivering for the last 25 years. So okay, so that's my pitch on the value of RHEL in the context of OpenShift. There's more stuff, but you're gonna have to wait for the next time because I don't have time. So I'm gonna stop there.
I think we'll give you a whole hour next time.
I'll take it.
Thank you. So David, I know you had a question. Would you like to ask it? If you're still there. Otherwise, we can go back to Jerry's question. We have 3 minutes, so I think we have time for one question, unless Mark, you have something that you want to talk about.
I was just gonna say we know Jerry, and we can follow up with Jerry offline on the kernel driver stuff. But that is certainly, that's definitely one of the use cases that helped drive this. We believe the best customer experience is the inbox drivers that we ship as part of our kernel, but we also know the reality of customer needs, and that's just not always practical. And yeah, I'll just echo what Gunnar said about, we are built off of the same battle-tested components that are run in all types of environments. RHEL is a general purpose OS that gets, I won't say attacked or whatever, it gets used in anger in many different ways. And so we benefit by basing OpenShift, all that chain from the kernel through the container runtime up through your containerized app benefits from all that kernel work and all that OS level work. Probably that base layer, the compatibility stuff, by the way, probably all of those are in CoreOS. That's probably about half of what it is, right? And a fair amount of the useful stuff.
Yeah, one thing I would add to that briefly, to build on what you said and what Gunnar was saying is and I think we should emphasize more. One thing that's very technically cool about with CoreOS layering is that single container image runs exactly the same in bare metal, vSphere, AWS. You can build a derivative of that with your custom kernel. And we have customers that do this, like deploy CI environments in vSphere, take that exact thing and deploy it on Metal. And then there's some compromises in this because we actually ship the VMware agent in that image. So it's there, even in AWS, it's just off, but it's pretty powerful. There's one thing that runs everywhere.
Yep. The only difference between images that we truly have is chip architecture. So there may be different packages for power than x86, but otherwise they're bit for bit on every platform.
So we have one.
I'm happy to come back later and do a full RHEL clinic if people have got an appetite for that.
We may have a really quick, quick question. It's about your mission statement, Gunnar.
Mm-hmm. Yeah.
So David is one of our community members that has been working on figuring out some edge architectures for incident management.
Yeah.
And so his question is, one of the statements that you want Rel everywhere, et cetera, and Rel is already working in the Department of Defense space, now telecom, and seeing that you're having more and more public safety incidents in Rel. Are you looking, am I capturing this correctly, David? Are you looking at that space and incident management spaces?
Yeah. So, something really interesting is happening right now with, you probably saw the news on RHCOS, right? The Red Hat in-vehicle operating system. We talked about that at Summit last year. And the irony is we went through internally, and I think Mark, you were in some of these conversations, we went through a whole bunch of very careful, okay, we're gonna do this automotive stuff, but we cannot let the automotive stuff derail or contaminate the regular rail business, because this stuff is absolutely terrifying. There's going to be functional safety requirements, and it's going to completely send us off in the wrong direction, right? We don't want to get distracted by this and take away from the core rail mission. Turns out we didn't need to worry about that. The joke's on us, because actually we were able to do almost everything we needed to do in this in-vehicle operating system, and with these functional safety requirements, we're able to do almost everything that we need to do without wildly deviating from regular RHEL, which is enormously satisfying to me and has given me a lot of confidence in the fact that, there may be certifications that we need, there may be documentation that we need and things like this, but it is possible to take all the goodness that we are doing in RHEL today and be able to expand into these other more demanding markets without too heavy a lift. And I think that's rad. I think that is super cool. And I think the technology that we talked about today, right? Not just creating a CoreOS, but also making CoreOS more manageable and more customizable for weirdo situations. Let's go take CoreOS and use CoreOS layering to go manage a car, or stick it in a satellite, or embed it in a safety critical system. That is way less crazy now than it was maybe 5 years ago. So to answer your question, yeah, we're absolutely looking at that. Yeah.
I just want to add to that too. Actually, there were a couple of technological improvements that came from the RHCOS effort that
Yes.
that ended up benefiting RHEL. If anybody's familiar with Podman, check out Quadlet, which is a new feature that's going to be GA in the next RHEL minor. But my point is that it adds this ease of use, and that came from the RHCOS effort. ComposeFS was also, at least some of the work was driven by that too. For people who are really interested in the future, go check out ComposeFS on GitHub. So yeah, it's really actually paid back RHEL in turn.
Yeah, and this is the last grace note I'll put on this, just to kind of put a punctuation mark on this. This is what is so cool about this relationship between RHEL and OpenShift, is because OpenShift is able to directly benefit from all of the exposure and the breadth of the RHEL audience and the breadth of the RHEL reach, so that when somebody is running RHEL in a car and we get an improvement on that, that is able to carry straight into OpenShift, right? Real-time is a classic example of this. Real-time was created by IBM and Raytheon to go build a destroyer for the US Navy. That technology ended up being used instead by financial services and on Wall Street, and now it's being applied to telco, right? And that is because they made the deliberate decision to not do a purpose-built operating system for one task, but because they wanted to make sure they had a general purpose operating system that could do this incredibly specialized work, so that when we built real-time in one place, it actually has dividends for other markets. And that's what you get access to when you base a container host on something like RHEL. It's awesome.
Thank you. I know we're running over. Thank you so much. We can definitely have another hour of real time. Appreciate you joining us. And all the talk about RHCOS layering, definitely one of the technologies that I am most excited about. I know it's weird, but hey. All right. And then in 2 weeks, come back and we're going to have a discussion on Edge. So thank you, everyone. And I'll submit the recording to YouTube. All right.
Thanks a lot.